Right, so in this video, I'm gonna be explaining another important article with the title Deepwalk Online Learning of Social Representations. So, this is an old article in 2014, but it historically is very essential. So, we present Deepwalk, a novel approach for learning latent representations of vertices in a network. These latent representations encode social relations in a continuous vector space, which is easily exploited by statistical models. Deepwalk generalizes recent advancement in language modeling and unsupervised feature learning from sequences of words to graphs. Deepwalk uses local information obtained from truncated random walks to learn latent representation by treating walks as the equivalent of sentences. We demonstrate Deepwalk's latent representations on several multi-label network classification tasks for social networks such as Block Catalog, Flickr, and YouTube. Our results show that Deepwalk outperforms challenging baselines which are allowed a global view of the network. So we seek the learning social representation with the following characteristics: adaptability. Real social networks are constantly evolving. New social relations should not require repeating the learning process all over again. Also, community aware. The distance between latent dimensions should represent a metric for evaluating social similarity between the corresponding members of the network. Low dimensional. When labeled data is scarce, low dimensional models generalize better and speed up convergence and inference. Continuous. We require latent representations to model partial community membership in continuous space. Having chosen online random walks as our primitive for capturing graph structure, we now need a suitable method to capture this information. If the degree distribution of a connected graph follows the power law, that is scale free, we observe that the frequency which vertices appear in the short random walks will also follow a power law distribution. Word frequency in natural language follow a similar distribution, and techniques from language modeling accounts for this distributional behavior. To emphasize this similarity, we show two different power law distributions. The goal of language modeling is to estimate the likelihood of a specific sequence of words appearing in a corpus. So, given a sequence of words, we would like to maximize the probability overall the training corpus. So we present the generalization of language modeling to explore the graph through the stream of short random walks. These walks can be thought of short sentences and phrases in a special language. The direct analog is to estimate the likelihood of observing vertex vis-a-vis given all the previous vertices visited so far in the random walk. Our goal is to learn a representation, not only a probability distribution of node occurrences, and so we introduce a mapping function phi. This mapping represents latent social association with each vertex. So, however, as the walk length grows, computing this objective function becomes unfeasible. A recent relaxation in language modeling returns the prediction problem on its head. First, instead of using the context to predict a missing word, it uses one word to predict the context. So solving this optimization problem builds representation that capture the shared similarity in the local graph structure between vertices. Vertices which have similar neighborhood will acquire similar representation and allowing generalization on machine learning tasks. By combining both truncated random walks and neural language modeling, we formulate a method which satisfies all of our desired properties. This method generates representations of social networks that are low-dimensional and exist in a continuous vector space. So the algorithm is called deepwalk. It consists of two main components. First, a random walk generator, and second, an update procedure. The random walk generator takes a graph, samples uniformly a random vertex v sub I as the root of the random walk. A walk samples uniformly from the neighbors of the last vertex visited until the maximum length is reached. While we set the length of our random walks in the experiments to be fixed, there is no restriction for the random walks to be of the same length. These walks could have restarts, but our preliminary results did not show any advantage of using restarts. Skipgram. So they shuffle, and then after random walk, you give it just to the skipgram algorithm. And I've explained skipgram in a different playlist, I think 2 years ago, on natural language processing playlist. So we think of each iteration as making a pass over the data and sample one walk per node during this pass. At the start of each pass, we generate a random ordering to traverse the vertices. This is not strictly required, but is well known to speed up the convergence of stochastic gradient descent. So a skipgram is a language model maximizes the occurrence probability. And it has some problems. That's why we have negative sampling, hierarchical softmax, in order to manage the problems that the denominator is producing. So hierarchical softmax is one of them. And then we can also do this in parallel. So these are only 3 data sets that they have done for deepwalk. Some of them have 1 million vertices. For YouTube, it has 1 million vertices, huge. So you cannot do this with conventional graph neural networks. You need something like deepwalk to be able to do this. Also, if the graph keeps changing and changing, still this algorithm is good enough. Although this paper is for 2014, but it's still very powerful. And so this paper is only focused on multi-label classification. It's not about graph classification because, for example, graph classification datasets like protein have very small number of nodes. But multi-label classifications like YouTube, YouTube has 47 labels and 2 million edges. 1 million nodes, 2 million edges, 47 labels of each node. So it's a really hard algorithm. So if the percentage of labeled nodes grows, for example, if you use even 90% of label nodes, still the result is not so good. It's only 42. Event spectral clustering gives the same result. And the modularity objective is even worse. But this is micro. The macro one is for deepwalk is 28. So about Flickr is also another very hard data set. And for deepwalk, if you have 10% of nodes, labeled nodes, then you have 38 accuracy, 25 for deepwalk. But for spectral clustering, it's worse. Spectral clustering is worse.